completed his PhD in 2017. Both are from NIT Raipur. Following his doctoral studies, he worked as a postdoctoral fellow at IIT Bombay from 17 to 19. Subsequently, he held the position of assistant professor at Kalinga Institute of Technology, University Bhubaneswar from 2017 to 2022. Dr. Shivam Gautam's expertise lies in the field of power converters, control, and their applications. Over the past decade, he has dedicated his research efforts to power electronic converters used in photovoltaic systems and electric vehicles. In recognition of his outstanding performance during his master's research, he was honored with the POSOCO Award by the Government of India in 2014. Moreover, he has published 15 research papers in renowned journals within his research domain, including IEEE transactions and IET power electronics. Additionally, Dr. Shivam Gautam has secured funding for 2 projects from SERB, Science and Engineering Research Board, each spanning a duration of 3 years. These projects contribute to his ongoing research endeavors. Furthermore, he recently received the prestigious 2020 IET Power Electronics Premium Award for one of his published works, highlighting his significant contributions to the field. Furthermore, Dr. Shivam Gautam has been granted 3 Indian patents, all related to power electronics converter topologies. With these credentials, I'd like to welcome Dr. Shivam for his respected talk. Start.
Sure.
Yeah.
Sure. Thank you, Professor Thirumurugan, for a nice introduction, and we'll start the presentation. So allow me to share my screen. My screen is visible, Thiru sir?
Yes, Paka.
Okay. So, once again, a very good evening to all the participants, and today I will be delivering a very small lecture of 1 hour on multi-level converters in electric vehicles, not specifically drives, but you can say electric vehicles. So, as my introduction already has been done, so I will skip this. So these will be contents of today's presentation. I will give a very brief review in a block diagram way that what are the various power converters which are currently used in EV. Then we will have a look into the 2-level inverters, because without appreciating the 2-level inverters, one cannot move to the multi-level inverters. So we will see what are the problems because of which there has been an invention of multi-level inverters. So we will have a look into the multi-level inverters, and then we will see the drawbacks of multi-level inverters that is basically a conventional multi-level inverters which have been invented in early 1980s or 1970s, you can say, 40 years, 50 years from now. So there are the drawbacks of multi-level inverters, because of which the researchers or research domain in the past few decades have tried to develop some of their own topologies. So we will have a glance of some of my work which has been presented in some of the journals, And then we will have also a look into the fault tolerant multi-level inverter topology. Fault tolerance is very much essential when we talk about multi-level inverters, because in multi-level inverters the number of semiconductor devices will be increased, and the you can say the reliability of semiconductor devices cannot be predicted, and so there is likely chances that if you are using hundreds or thousands of semiconductor devices uh, in any converter topology, some might fail. So you should have uh, a topology which can be able to work even after the fault. So that is why that term is there, that is fault tolerant. I will come back to this fault tolerant term again when we will discuss. Then I will conclude by having some conclusion and challenges currently which the research community is facing in power converters, specifically in multi-level converters. Now, during my presentation, I will, if any of the participants have any doubt, they can stop me and ask the doubts, uh, or they can also discuss the things if they have any issues. So we'll start with introduction of power converters for EV. So as this whole 5-day program is related to EV, so I will not be discussing much about the different parts of EV, but I will briefly discuss. Right. So electric vehicles relies on power converters, as we have already seen in the yesterday's and today's session. The power converter is the heart of electric vehicles. Right. For efficient energy management and control, power converters are essential for converting, controlling voltage, current, and frequency in the electric vehicle system. Right. So uh, this is the very basic, you can say, overview or block diagram view of the power flow in in power flow in electric vehicles. So starting with the grid side, so you can see here we are having a single phase or three phase supply in this part. Then, if you want to charge your battery, you first need to convert this AC supply to a DC supply. So we will be requiring some kind of converter. So here we will be having AC to DC converter as well as PFC controller. That is power factor corrector unit is also required, so that less amount of harmonics can be injected back to the grid. Uh, so this is AC to DC plus PFC converter we say. So this is unidirectional converter as of now in this figure. So this is a unidirectional converter, means the power can flow only in one direction, that is from grid to the vehicle. And then here we are having a DC to DC converter. You can see, so here we will be getting a DC, and when you need to charge a battery, so we will be using a DC to DC converter. As of now, the most famous is DAB converter, that is stand for dual active bridge. Basically, it consists of a 2H bridges, and in between we use a high frequency transformer the high frequency transformer is used to up and down the voltage, to get a voltage regulation, right? So so this is regarding the this DC to DC converter, and then this is a DC bus which can be around of 600 volt or 600 volt or 400 volt, or right now the research is moving towards the 800 volt as well, 800 volt as well. So depending on the application, we can have different DC voltages here. Now, if you want to run an AC motor, such as an induction motor, you need to again convert back this DC to an AC, right? So here we will be requiring a DC to AC converter. So this is also a bidirectional power electronic converter. Bidirectional means power can flow in both the ways, right? So if you are applying a regenerative braking, then power can flow back to the battery as well. So this is a bidirectional converter. Apart from that, here also you can see one converter is there. This is also DC to DC converter. This 600 volt can be an unsuitable for the auxiliary or the other electronic components, like music system is there, headlights, lights, lightings are there. So if you want to run that, so you need to step down this voltage. So again, DC to DC converter is used here. Okay. Now, if you see the theme of today's presentation is multi-level inverter. So Where can we use multi-level inverter? As of now, multi-level inverters can be used in our this motor drive system. We can use a multi-level inverter. I will discuss the multi-level inverter in detail in coming slides, but we can use this multi-level inverter here. We can also use multi-level inverter or multi-level converter here as well. And recently, the researchers have suggested that we can use multi-level inverter here as well in power factor corrected unit as well. So if you see the scope of multi-level inverter in EV, the researchers are, or the research trend is showing that we are moving ahead with the application of multi-level inverters for EV. Yeah, okay. As I told you that we are slowly moving to 800 volt DC line. So for controlling this 800 volt, definitely multi-level inverter will be used or will be required, right? So so you can see that the multi-level inverters we can use in different parts in the electric vehicle as well. So with this information, again, this is very brief. I know many of us might be aware, but just let us have a look into it before going deep into the concepts of multi-level inverter. So what is an inverter? So DC to AC inverter convert the DC power from the battery into an AC power to drive the electric motor, right? Because the motor which we are using is AC motor, right? They play a crucial role in controlling the speed and torque of the motor. So this is well aware fact. A PWM technique is commonly used in DC to AC inverter to regulate the output voltage and frequency. So PWM stands for pulse width modulation. So it is a, you can say, a controlling technique which is used to control the on and off of the switches, semiconductor switches which are used in inverter, right? So this is a controlling technique, we can say, which is used to control the output voltage, that is RMS voltage and frequency both. So it involves rapidly switching. It involves rapidly switching the power semiconductor devices on and off to create a pulse waveform, right? So this pulse width modulation creates a switching pulses which switch on and off the semiconductor devices which are there in the inverter. So three-phase inverter, what is three-phase inverter? Three-phase inverter is a type of DC to AC inverter commonly used in electric vehicles. It generates three-phase AC power to drive the electric motor. The three-phase inverter consists of a power semiconductor switches that control the flow of current to the motor windings. So instead of a single phase, we are using a three-phase inverter for better power control. Now, first type of inverter that I will be discussing here is two-level inverter, two-level three-phase inverter, you can say. So if you see, I know many of us are from electrical background, and all of us have studied in undergraduate as well as research. If you are doing research, you might have already gone through this converter topology. So let me briefly explain this again. So this is leg 1, leg 2, and leg 3. Three legs are there, and in between each leg, you can say a wire is coming out, and here you can connect your three-phase motor. As of now, I have connected a load, right? Now each leg consists of two switches. You can see S1 and S2, and these two switches are complementary in nature. Complementary in nature means these two switches cannot be turned on at the same time and cannot be turned off at the same time. So at any instant, any one of the switch has to be on, right? So these two switches are complementary in nature. Now in these switches we will give how to turn on and turn off this switches. We will give the gate pulse through gate drive, okay, and with that the switches can be turned on and off. And the technique that we will be using for generating this gate pulse is called as PWM technique, that is pulse width modulation technique. So the takeaway from this slide is this is a two-level inverter. Why two-level inverter? Because it can produce, if VDC is the input voltage, it can produce two levels only, that is plus VDC and minus VDC. So therefore we are calling it as a two-level. So we will see in coming slide as well. So if you see this, these are the line voltages of the two-level inverters. Purposely I have included this So this voltage, if you see this cut, so this is 500 volt minus 500 volts. So you can see it is going from plus 500 volt and minus 5 to minus 500 volt. Line voltage, A line voltage, B and C, and each are 120-degree phase shifted. Now if you look closely, you can see the duty cycle or the width of this pulse are changing, and when it gets to center, the width is maximum, and again the width is decreasing because it is imitating a sinusoidal voltage. It is imitating a sinusoidal voltage like this, right? So therefore we are calling it as a pulse width modulation, because you can see this is acting as a pulse and the width of the pulse is changing, and to get the maximum amplitude or magnitude, the width of the pulse is maximum at the center, and to both sides of the center the width is decreasing again. Similar pattern can be observed in the negative cycle as well. You can see the pulse width. So therefore I hope the term pulse width is clear. So this is 500 volt, and second important point is you can see that it is going from plus VDC, this plus VDC to minus VDC. There is no intermediate voltage level which is present here. So therefore it is called as two-level inverter. Am I audible properly?
Yes, yes.
Okay.
Yes, Shivam.
Okay. So this is the output of three-phase two-level inverter. How does it looks like? Now this slide I have also purposely included. So this is the harmonic profile of the output waveform that we have just seen. So harmonic profile of this waveform, how does it look like? So it looks like this. So this is a simulation result from the MATLAB. So you can see 500 volt is the DC voltage that we have provided. This is 500 volt. The fundamental voltage that we are getting is 430 volt. That is at 50 hertz frequency. If the reference frequency is 50 hertz, so at 50 hertz we are getting 430 voltage, and the THD is 69 or approximately 70%. So keep this number in mind. The THD is 70%. So generally IEEE standard says the THD should be less than 5% for voltages. For voltages, THD should be less than 5%, and for current the THD should be less than 2 or 3%. And as of now, we are getting a 70% THD in the output voltage profile of a two-level inverter. So we can use passive filters to remove the harmonics that we can definitely use. So this is one of the drawbacks of a two-level inverter. Now this slide is also very important in order to appreciate the multi-level inverters. So if you see here, this voltage is 500, this is also 500, and this is also 500. So this is the blocking voltages. This is the blocking voltages of three legs. So the upper row shows the blocking voltages of leg 1 switches, because there were 3 legs in the two-level inverter. So this is leg 2, and this is similarly, this is leg 3. So 3 legs of inverters are there, and blocking voltages are shown. So you can see the blocking voltages. Blocking voltages means the amount of voltage the switch is blocking when it is off state. When switch is not on, so how much amount it has to block. So if you see, if S1 is off, let us say if S1 is off, then it obviously it has to block 500 volt. And as I told that if S1 is off, S2 has to be on, right? Both cannot be turned off at the same instant, as well as both cannot be turned on at the same instant, right? So at any instant, any one switch has to be on. So if S1 is off, it has to block 500 volt. That means this switch should have the capability to block 500 volt. So that is what is reflecting here in the blocking voltage. So here, keep in mind that the blocking voltage, the switch is going from 500 to 0. What is the transition from 500 to 0? And from 500 volt to 0 volt, it is going is in transition, right? So it cannot take place at the same instant, right? That means it will have some delay. It will have its own delay, right? Delay means time taken from going from 500 to 0. That means time taken from on to off. That is, when switch is on, how much time is taken to keep it in off mode, and if switch is off, how much time is taken to again bring it in on mode. In between, there is a delay time, right? Or you can say transition time is also there. So the time taken here will be, some time will be taken in order to go the voltage from 500 to 0 volt, as per the example that we are discussing. So these are the blocking voltages you can see, or you can observe for a three-phase two-level inverter. Okay, so two things to note here: the blocking voltage, it is going from 0 to 500 or 500 to 0, and the THD profile, that is 70%. Now let me just give you a brief about multi-level inverters. Then we will again come back to our problems of this 500 to 0 on THD. Let me just give a brief of multi-level inverters. In multi-level inverters, some of us might be already having expertise in multi-level inverters, but let us again give a very brief overview. So multi-level inverters provides solution to overcome the voltage restriction of classical two-level inverter. So when we talk about two-level inverter, there is a voltage restriction. What does this mean? So this means that, let us suppose I am applying a 500 volt here, and when switch S1 is off, so this has to block 500 volt, right? Now I can increase the voltage to 600 volt as well. If 600 volt I will be using, so it has to block 600 volt. I can go up to 1000 volt as well. If I apply 1000 volt, then it has to block 1000 volt. So up to how much voltage we can go? We can go up to 2000 volt, 3000 volt. So there will be some restriction, right? As of now, what I have seen, according to my experience, there is a 4.5 kilovolt of IGBT available in the market. 4.5 kilovolt, that is 4500 volt. So if you want to apply 5000 volt, you cannot apply because the switches are not there, right? The switches are not there. So there is a voltage restriction. So that is what the first term is. Multi-level inverter provides solution to overcome the voltage restriction. So with the help of multi-level inverter, you can apply a very high magnitude of voltage, right? A very high magnitude of voltage. And what can be the magnitude? That can go up to megavolt level as well, where we use modular multi-level inverters. The term is modular multi-level inverter, right? So we can go up to we can go up to megavolt level as well. Okay, so this is one of the restriction of classical two-level inverter. So multi-level, so that is why there was an invention of multi-level inverter, because the two-level inverters, there is a voltage restrictions problem. So multi-level inverters are basically categorized into three main groups. So these groups are, so they are divided, right, in three parts, or you can say three different researchers came. They have proposed their own solutions, and they have created a benchmark, right? So first is called as neutral point clamp. It is also sometimes called as diode clamp. We will discuss this topology one by one. Very briefly, we will discuss, obviously, because we have to cover other topologies as well. Another topology is flying capacitor, and third one is cascaded HVDC or CHV. So short form is also mentioned. So these are formed in between 1970s to 1980s, and these are called as classical or conventional. Classical or conventional multi-level inverter topologies. But these multi-level inverter topologies are having some you can say drawbacks as well, because of which researchers in the past few years have published some other topologies which are called as hybrid multi-level inverter topologies. Other than classical topologies, whatever topologies available in the market, they are called as hybrid multi-level inverter topologies. Okay? So hybrid multi-level topologies, it can have different characteristics based on the drawbacks of these topologies. These topologies will have some drawback that we will see again briefly in coming slides. Based on the drawbacks, new topologies are proposed in the literature, as well as it is also used in the industries. And as I told you in starting as well, as multi-level inverter uses number of switches, that is the number of switches will be more, so there is always the chance of fault. So if a critical application is there, so the topology one should propose or one should develop should have the capability of fault tolerant. Now fault tolerant topology can again be further divided into partial fault tolerant and complete fault tolerant. So partial fault tolerant means, suppose under normal you are operating at some power, and after fault has occurred, the power has reduced. It cannot, your converter cannot operate at that power level. So that kind of topology or solution, which is called as partial fault tolerant, that is not working. The post fault is not working exactly same as pre fault condition. And second one is complete fault tolerant, where power will be same post fault and pre fault both. So this is the regarding some description about the multi-level inverter. Now this is a graphical picture which shows the you can say classes of multi-level inverters. So DC to AC power converter. So this is inverter current source and voltage source can be further divided. Current source has not gained much of the you can say advantages or traction. So therefore, people have moved towards the voltage source inverter. Two-level inverter we have already seen, and multi-level inverter. Since the topic of discussion is multi-level inverter, therefore I have classified multi-level inverter into the different categories. You can see, so fault tolerant, flying capacitor, CHP, and neutral point clamp. These are our conventional topologies where this have been proposed recently, hybrid and fault tolerant. So fault tolerant again can be divided into partial and complete. And cascaded can be further divided into symmetrical and asymmetrical. We will discuss in coming slides. And neutral point can also be divided into multiple DC source and single DC source. Partial fault tolerant can further be divided into. You can develop solutions of giving the or increasing the fault tolerant capability of conventional topologies, or you can propose your own topology. Then in that case, it will be called as hybrid topology. Again, complete fault tolerant can be developed for conventional as well as for your own topology. Based on that, there are some. So there is a 3-leg NPC with additional hardware. Some of the work which has already been done in the literature has been noted here. Hybrid topology can be divided further into the multi-level inverter with reduced devices. We can reduce the number of DC sources by innovative topologies. We can reduce the number of switches, or we can reduce both the DC sources and switches. So this is how the multi-level or classification of multi-level inverters comes in. Now moving to the multi-level inverter, the first topology that I would like to propose to you or explain you about is a T-type multi-level inverter. So why it is called as a T-type inverter? Because if you see this section, so this looks like an alphabet T, right? So therefore it is called as T-type multi-level inverters. So if you see, this portion is similar to a two-level inverter that we have already seen. In addition, we have added a bidirectional switches. You can see we have added 3 bidirectional switches. Bidirectional switches means that it has the capability of blocking the voltage in both the direction as well as conducting the current in both the direction, right? Okay, so these switches are S1, S5, S9, S4, S8, and S12 are unidirectional switches. It can only block the voltage in one direction only, right? If you apply the voltage like this, then this will not be able to block the voltage. Rather, the diode will conduct, right? So this can only block voltage in single direction. Whereas this, if you see, this is having the capability of blocking the voltage in both the directions. So therefore, it is called as bidirectional switch. So each bidirectional switch is connected with the midpoint of the capacitor and to the midpoint of the leg. So you can see each capacitor is connected to the midpoint of two capacitors, and each midpoint of the one leg. So this is the topology of a T-type multi-level inverter. Again, we can use the pulse width modulation technique to get the appropriate waveform. And how does the waveform of P-type inverter look like? So it looks like something like this. So again, if you apply a 500 volt DC, like in previous example in 200 volt, so you can see we will get the 500 volt here as well. But instead of going 500 to minus 500, it is going some in form of steps. So from 500 it is gone to 250, and from 250 it has gone to minus 250. You can see minus 250 and to minus 500. So it is going in form of steps, right? What is the advantages of going in form of steps? Or more importantly, what is the advantages of two T-type? Why anyone will use T-type inverters when two-level inverters are already present in the literature? So this is the question one should ask. So one thing is that we are getting the waveform in step. What is the advantages of getting the waveform in step? So one basic advantage is that the THD is reduced. You can see in two-level inverter the THD was approximately 70%. And this in T-type inverter, the THD has reduced to almost half. That is 36.5%. Again, this is a simulation result. The experimental results the THD can vary. 10% THD can also vary. So that means instead of 36, you can get 38 or 39% THD as well. Not more than that experimentally. Since this is a simulation, ideal parameters have been considered. So the THD we are getting is 36.49%. That is almost half of the THD. What will be the advantage? The direct advantage we see here is the reduction in the filter size. Size of the passive filters, which LNC, which we are using, will be reduced. Also, if you see the fundamental is 427 volt here. This is one of the advantages that we are getting reduction in THD. Go for T-type inverter. Okay. So this slide shows again the blocking voltage. Okay, blocking voltage of leg A, leg 1. So this both consist of leg 1. This is leg 2, and this is leg 3. What is the distinct difference you see here? So this is 500 volt, and this is 250 volt. So this is again 500 volt and 250 volt, so on. So what is the distinct difference you see? In two-level inverters, the voltage blocking voltage is going from 500 to 0 volt. Whereas in two-level inverters, it is going from 250 to 0 or 500 to 250. So one can see that because of this, since the voltage is going from 500 to 250, the delay will be less. That means you can operate at a higher switching frequency. The delay will be less, right? Small time will be, or half of the time will be required as compared to going from 500 to 0. Right? So delay will be less. Another advantages can be stresses on the device. If you see in two-level inverter, we were going from 500 to 0, whereas here we are going from 500 to 250 only. So the stress amount on the device is also less, which increases the reliability of the semiconductor device. So this is one of the factor of the malfunctioning of the semiconductor device. Due to the over stress of the semiconductor, there will be chances of malfunctioning, right? So because of this, we have reduced from 500 to 0, we have reduced to half. So it is going to. Another advantage can be low EMI, that is electromagnetic interference, when you compare with the two-level. So EMI is also one of the key aspects of power electronic design, where you do not want that your power electronic converter should interfere with the other components in the nearby vicinity, right? So if you are switching from 500 to 0, and if compared that with 500 to 250, so 500 to 250 will have lower EMI, right? So we have seen that 3 or 4 advantages of P-type inverter when we compare that to the two-level inverter. Right? Second multi-level inverter topology that I want to discuss is neutral point clamp. So neutral point clamp, or NPC topology, or it is also called as diode clamp. In the name itself, it is defined, that is, it is diode clamp. We will discuss. So you can see again, if you apply a 500 volt here, just as an example, so each capacitor can have a value of 250 by 2. Sorry, 250 volt. 500 by 2 is 250. And you can see that here 2 devices are connected in series. So if both the devices are off, both S1 and S2 are off, that means both S1 and S2 have to block 500 volt. But what is the advantage of this? You can see that we have connected a diode here. So with the help of a diode, there is a path. So you can see there is a path due to which the blocking voltage of this switch has been clamped to 250. That means this switch cannot have more than 250 volt of blocking voltage. So each of the switch will have 250 volt, because ultimately it has to block 500 volt. Each switch has to block 250 volt. If you directly connect two IGBT in series, then there will be a chance of malfunction due to the transient. The blocking voltages might shift, right? But here, due to the presence of diode, this switch has already clamped to 250 volt. It cannot deviate from 250 volt, right? It cannot go more than that. Or if this capacitor voltage is increased, so if this capacitor voltage can only increase in case of fault, or if you increase the input voltage. So that is why this topology is very famous, and it has got a lot of uses in industries and electric vehicles as well. This is the neutral point clamp topology. Second type of multi-level inverter topology is neutral point clamp. Just a second. Okay. So you can see these are the diode. So these are, because of this is called as clamped diode or diode clamp. Because of the diode, the blocking voltage of this switch is clamped to the voltage of this capacitor. The voltage of this capacitor will be VDC by 2. This again, by this animation, it is trying to show that this switch, if it is off, has to block this VDC voltage. But if this, you can see if this switch is on, then this switch has to be off. Then due to the presence of this diode, you can see this diode, this anti-parallel diode and diode D2, the switch of the blocking voltage of this switch will be clamped to the voltage of this capacitor, which is obviously 250 volt. This is how we can make a three-phase neutral point clamp. So this is again three legs are there: leg 1, leg 2, and leg 3. Right? Again, we can provide suitable PWM technique to switch on and off these switches. Okay. And how does the waveform of this looks like? So you can see this is the waveform of two-level of NPC. That is neutral point clamp converter. Again, if you observe, instead of going from positive to negative, it is going in form of steps. So as we have seen in T-type inverter, this will also have a lower THD. So you can see the THD is almost half of the two-level inverter, which is 35%. Right? This is a significant advantages of NPC converter. Now this is very important. This is again the blocking voltage profile. So you can see this is 250 volt. Between 200 to 200, so this is 250 volt. So that means 4 switches which are used here, you can see in one leg. Each switch will have 0 to 250 volt only. It is going from 0 to 250 volt. Each switch is blocking up to 250 volt, as I have discussed here only, here as well. Because of this diode, the blocking voltage of this switch has been clamped to 250. It cannot go beyond 250 volt. So that is what has been shown in. So this is the blocking voltages of one leg. 4 switches are there in one leg. If you can see, 4 switches are there in one leg, and blocking voltages profile of all the 4 switches, it is going from 0 to 250 only. If you compare this with the two-level inverter, we were going from 0 to 500, whereas here we are only going from 0 to 250 only. Also, if you compare this with T-type inverter, there you need to have blocking voltage capability of 500 volt switches, right? The leg switches has to block 500 volt, whereas here only 250 volt is up to 250 volt we can apply, right? The blocking voltage capability is up to 250 volt. So that means with the help of NPC topology, you can go to higher voltages. If with the help of two-level inverter, you can use 600 volt. With the help of NPC, you can go up to 800 volt or even 1000 volt or 1200 volt as well, depending on the available devices, right? So with the help of NPC, you go for higher voltage. Higher voltage means higher power, right? One can say that, sir, you can also increase the current limit to increase the amount of power, but if you increase the current, the sizes of the wire will increase, right? And due to which the losses will also increase. So it's better to increase the voltage than current. So this is a fact in power electronics. If you want to go for higher power, it's better to increase the voltage level corresponding in comparison to the current level. Okay. This is the 5-level NPC. Previously we have seen 3 levels, so this is 5 level. Generalized, or you can say we have expanded to more levels, right? More levels means more level. Why more level? Because again the input voltage is increasing. So from we can apply 2000 volt or 3000 volt, right? And because of which the blocking voltages of each switch has been clamped to the voltage of these capacitors, right? If 2000 volt is applied, each capacitor will have 2000 by 4. So 2000 by 4 will be 500 volt. So each switch will have the blocking capability of 500 volt. So this is the switching table. You can see you can get 0 volt by not switching on any of the switches. That means S1, S2, S3 will be all 4 will be off. That means these are complementary switches. So S1 and S1 bar, these are complementary. S2 and S2 bar is complementary. If all are above switches are off, that means all the below switches are on. If you want to get VC, then S4 needs to be on. So S4 is this switch. You can see I will explain for one level, that is VC. So S4 is this switch. So how the current will flow? So current will flow from here like this. It will flow from diode, and this S4 is on, so it will go from switch S4 and then to the load. Right. So what is the voltage that we are getting? Voltage is CV. Whatever the voltage of CV, which is VDC by 4, which we will get in the output voltage. Right. So similarly, you can say use different switches to get different levels, right? So this is the extension of our NPC topology. Next, classical topology is flying capacitor topology. Instead of connecting a diode, here we have connected a capacitor. This is a conventional topology. Again, if VDC voltage is 500, this capacitor voltage will be 250, right? And because of which the blocking voltage of this switch is again 0 to 250 only, right? Uh, Here also you can generate output levels, output voltage in case of staircase waveform, right? As a staircase waveform. So this is a flying capacitor topology. Next one is H-bridge topology. It is having the structure like an H bridge of an English alphabet. Therefore, it is called as H bridge, right? It is having 4 switches. You can switch on the switches in combination to get the output voltages accordingly. So we can get output voltage of Vs, minus Vs, and 0. So these 3 voltages we can get. If you want to get Vs, you can switch on switch S1 and S4, right? You can get Vs. If you want to get 0, you can switch on S3 and S4. So we will get 0, and if you want to get minus Vs, you can switch on S2 and S3. So we will discuss this. So you can also extend the H bridge topology. So for symmetrical multi-level inverter, the number of output levels is 2n plus 1. Any doubt is there from anyone? Okay. Where n is the number of H bridges.
Shivam, sorry for the interruption. We have 5 more minutes for you.
Okay. So number of output levels is 2n plus 1 for symmetrical. So if H bridges, if you use one H bridge, then output levels will be 3. If you use 2 H bridge, number of output levels will be 5. So as you move towards the higher number of levels, the amount of THD will be less. You can also use asymmetrical multi-level inverter. In asymmetrical multi-level inverter, what we do, we use a variety of DC sources, right? And the value of DC sources can increase in a form of 2:1 or 3:1. Obviously, in 3:1, we will get more number of levels. Suppose if you use 2 H bridges, so number of levels that we can get for asymmetrical will be 9, as compared to the 3 levels that we are getting for the symmetrical multi-level inverter. So you can see the amount of THD will go down further. So this is a cascade connection of H bridge. 2 H bridges are connected in cascade manner or series manner, you can say. And so I will explain. If in order to get 0 voltage, you can switch on lower switches. If you switch on lower switches, you will get 0 voltage. If you want to get VDC voltage, you can switch on either the top diagonal switches and bottom switches, or there is alternative path as well. So I will discuss this path. That means you can either switch this strategy or this. So in 2 ways, you can get VDC voltage. You can see in this way also you can get VDC voltage. For getting 2 VDC voltage, you can switch on S1 and S4 and S5 and S6, so on. So there is a concept of redundant paths here. So redundant paths means more than one way you can obtain the same level. So these redundant paths are very useful in case of fault. So suppose if you encounter any fault in switch S1, right, then you can get the same VDC level by switching to this technique, right? By utilizing this switching, you can get VDC as well. So you can have the capability of fault tolerance. Equal power balancing. Equal power balancing means here you can see this is a DC source. It can be in a battery as well, right? So with the help of this redundant paths, we can use the battery in equal amount. That means we do not want one battery to drain off first or quickly, and then the second battery will be used, right? So we want the amount of discharge in each of the battery at the same rate. So this can be possible by using the redundant paths. Equal SUR. SUR means switch utilization ratios. So here we are having switches, right? We do not want one switch having more transition as compared to the other switches, right? We want the transitions. That means transition means switching on and off. We want on and off of each switch at the equal rate, right? So we can use this redundant paths for equal switch utilization as well. And this redundant paths will also be used for space vector modulation. So this is a type of modulation other than pulse width modulation, where you can generate the output voltage level. So there also these redundant paths are very useful. So this is the output waveform of a 5-level inverter. So you can see we are reaching to the positive to negative in step of 5. So this is first level, second level, third level, fourth level, and fifth level. So this is having the THD profile. You can see 27.49, which is further reduced. Obviously, the size of the filter will also goes on reducing. Now you can connect many of the CHP devices in cascade. You can see many of the many of the H bridges are connected in cascade manner to generate more number of levels. So some of the drawbacks of multi-level inverters or conventional multi-level inverters are one of the drawback of NPC is that it suffers from unbalancing of capacitors. We have seen capacitors in our NPC topology. If you move above 3 levels, let us say if you want to move to 5 levels, then there will be a problem of capacitor unbalancing, or you have to use a more sophisticated technique to balance those capacitors. Another disadvantages of NPC is that higher conduction losses of the inner devices. So if you recall, the NPC's leg of NPC is having 4 switches, 2 outer switches and 2 inner switches. So the 2 inner switches will have more conduction losses because it will be on for higher amount of time as compared to the 2 outer switches. So if one of the devices is conducting more, then chances or probability of having fault on that device will be increased, right? So there in NPC, equal switch utilization ratio cannot happen, right? So this is one of the disadvantages of NPC. Flying capacitor requires large number of capacitors. So this is a disadvantage of flying capacitor, and pre-charging of for higher number of levels. So you need to pre-charge the capacitors of flying capacitors, otherwise there will be a voltage and current spike at the starting. If you talk about CHB, it requires isolated DC sources. So this is the disadvantage of CHB. So all in all, what we observed is that the conventional topology require a large number of switches, right? If you want to move to higher voltage level, or if you want to generate voltage waveform of having less THD, then you have to use a higher number of switches. And if you use higher number of switches, so there will be so this will higher number of switches will require a higher number of gate drives, and the size of the heatsink will also be increased, because of which the cost will also increase, and losses, if you are using large number of switches, the losses will be less and the reliability will also go down. So these are some of the drawbacks. With this, I will stop here because of the constraint of the time. I would have loved to cover the recent topologies which I have included, but I will skip all those due to the limitation of the time. Maybe if you are having some doubt, you can email me or contact me, then I will be happy to discuss the recent development in the multi-level inverter topology. So this is, you can see this slide is instead of H bridges, I've used some different type of topology to generate 5 levels, right? So this is another type of topology which we can use to generate more number of levels, right? Then I have talked about fault tolerant. We can increase, so we can increase the fault tolerant ability of multi-level inverter by you can say changing some or doing some modifications in the legs. So you can see here I have used one leg of CHB and one leg of NPC. That means I have combined. Why I'm saying because the topologies are proposed by me. So I have combined one leg of CHB and one leg of NPC, and then for a single phase it will have a fault tolerant capabilities. So if you see the conclusion, so power converters plays a very crucial role in the efficient operation and control of electric vehicles. The ongoing research and development efforts are aimed to improving their performance, efficiency, and reliability. Moving towards 800 volt DC link that we have seen will be a challenge using wide bandgap devices, but still the work is going on. Moving towards the higher switching frequency to reduce the size of overall system, this is also a challenge. To move towards a higher switching frequency for a higher power level. Developing innovative topologies of power converters to support the need of the industry. So these are some of the challenges and as well as the future scopes of power converters if you talk in terms of electric vehicles. So thank you, and if you have any doubt, I will be happy to help if I can.
Yeah, thank you, Shivam. It was very technical as well as good for power electronics people. So questions are now open to us. In the chat also a couple of questions were raised. I will read for you, Shivam. A quick question is that THD dependent on the level of VDC, voltage source, the level of two level inverter.
Is THD dependent
Yeah,
on the level of VDC?
voltage source on the level two.
So THD is not dependent on the VDC voltage source. It is independent of voltage source.
Okay. The
Yeah.
second question asked by Pawan is, how does the number of levels in a multi-level inverter affect its performance and output waveform quality?
Yeah. If you have seen my previous slide, instead of two level, if you go for higher number of levels, so that will be more closer to a sinusoidal waveform, right? Because of which the THD becomes out to be low. If you go for 3 level, 5 level, 11 level, and if the number of levels still increases, then you will observe that the THD can be reduced to a greater extent. So this is one of the answer. And performance, obviously, if the THD is less, what I have observed is that the multi-level, these are low THD is a byproduct of a multi-level inverter. The main advantages why we moved toward multi-level inverter is that we want to apply a higher voltage. So we needed some topologies so that can support the higher voltages for higher power. So if you see the lower THDs, lower EMIs, and lower blocking voltages, these are the added advantages of the multi-level inverters.
Okay. So, any other questions?
Good evening, sir.
Good evening.
Sir, this you have not used inductor in your topology. How do you make this voltage and current ripple reduction? The new topology is what you have shown me.
Okay.
It doesn't have any inductor. I have seen only capacitor at the beginning.
Yeah. Yeah.
So,
Yes.
how do you make this current ripple reduction?
Current ripple reduction of output.
Yes, output side.
Output we can use filter, right? LC filter we can use. So here I have not shown the filter because that is very basic. So let's suppose we are having a two level output voltage. So this is a two-level output voltage. So after that we can connect a filter, LC filter here at this end to get. So here I have only shown the voltage waveform. Here I have not shown the current waveform, right? So if you want more sinusoidal current, more sinusoidal voltage, obviously we have to connect filters, second order filters. You can connect passive filters. You can connect.
Yes, sir. And one more thing is like the more challenging in any multi-level inverter is generating of gate pulses for the switching.
Yeah.
So, what are the new techniques that we can able to see nowadays in this generation of getting any other
So
strategy apart from this SPWM, PWM techniques? Any other topology that we have?
yes. See, the development of a new modulation strategy will be first you need to identify for a particular topology why you want to change the modulation first. Why you want to change the control strategy. First, you want to identify is there a really a disadvantage of certain modulation strategy. Suppose if you are developing your own topology, and for your own topology, the conventional modulation strategy is not working, then you need to modify the conventional topology, conventional modulation strategy to suit your topology. But if you see the conventional topologies and conventional modulation strategy, uh, you need to identify what are the first disadvantages of conventional modulation strategy. Then you can go and see. So the various modulation strategies are available, like level shifted, phase shifted, triangular waveform pulse, sawtooth waveform pulse, space vector pulse with modulation. Various modulation strategies have already been proposed. So what I feel that if you need to change the modulation strategy only if you develop your own topology. only if you develop your own work. Then for that you can develop your own modulation strategy and propose a new concept. Because for conventional it has already been done.
Okay, okay, sir. See, and one more thing is like, what is the power density we can expect, sir, if we wanted to go for this MLI? What would be the gradual power density that we can expect? Since I'm working on resonant inverters for high voltage generation, say as of now, I was working in resonant area for high voltage generation. I have taken 40 volts DC to convert into 4 kV. So I was working on that. So I already designed a hardware part and it is working fine, but the current density is very, very less because the quality factor is very high. So that is the issue I'm facing with. So what exactly the power density I can able to expect from LI?
Power density, if you talk in the actual hardware, so that I will not be able to tell, but you can increase the power density by moving towards the higher switching frequencies, because of which the if you move to the higher switching frequencies, that can be possible through the wide band gap devices. Then the sizes of the filters will be less. As I told you, that filters will be required here, so that size of the filter can be reduced.
Yes, yes,
Also,
correct.
if you go to the towards the higher power density, if you want to increase the switching, obviously if you want to move towards the higher power density, that means you have to increase the switching frequency, and the devices should support. And also the new devices which have come into the picture, they are having low losses like wide band gap devices, and we can reduce the size of heat sinks as well. So the comparison with the conventional silicon device, we can use wideband gap device to reduce the size of the filter as well as to reduce the size of the heat sink. So overall, the device will become compact, but there you have to see the thermal aspects as well.
Okay, are you saying that if I go for power density, this switching frequency plays a vital role?
Correct, very correct,
Okay, so
very correct.
if say for example, if I want to go for higher frequency, because in my resonant inverter, I just went for 90 kilohertz is the operating frequency. Generally, what is the normal range that we operate in MLI, sir? What is the critical switching
Normal
frequency?
range, what I have observed is up to 15 or 20 kilowatts, 15 to 20 kilowatts.
1.5.
1.5. What I have observed, what I have seen.
Fine, sir. Fine, sir.
Yeah, yes, because the power is very high.
Yeah. Okay. 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 So lesser the switching frequency, more the power density.
More the switching frequency,
No, no, less.
lesser the, yeah, you are saying the vice versa. Yes.
Yeah. Fine. 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 Got it.
Yes.
Sir, good afternoon, sir.
Good afternoon.
Sir, does the higher switching frequency affect the efficiency of our inverter?
Um, to some extent, yes, because the higher switching frequency will cause the higher switching losses.
Yes, sir.
Yeah, so the efficiency will go down. Then you have to select the appropriate device that can support up to that frequency, or you have to you have to go to the data sheets of the device, which device is having the smaller losses.
Oh, okay.
So if you
Okay,
go
sir.
towards high switching frequency, the loss will increase. That is very correct.
Okay, sir. If we want to use a higher frequency, switching frequency, then we need to select a device of means we need to
Yeah.
focus on the device.
Yes, because there are various devices which are available in the market, so you need to look into the data sheet.
Oh, okay, sir. Okay, sir.
Yes, yes.
Okay. Thank you, sir.
Thank you.
The chat, Mr. Musaf Ali has asked the THT requirement of less than 5%. Is this measured with or without load?
I think it is without load after the filter.
Okay. Musaf Ali, uh, is that answers you?
Yes, yes. Thank you very
Yeah.
much.
Okay. Yeah. Thank you. Faster as asked, will the loading of the device impact the efficiency?
Yes, yes. You have to obtain a curve that at what power level, what is the efficiency? Because the current will be changing. If you are applying higher load, the more current will be there. So you have to find an optimum point at up to what power level your converter is working. Right? You will get a U-shaped curve, and U is tilted towards the higher power. So if you have developed for 10 kilowatt, then you will observe that around 9 kilowatt the efficiency will go down. So up to 8 kilowatt or 7 kilowatt the efficiency will be maximum.
So another question posted by Vivek: why current THD is not in the picture of most MLI topology?
See, if you again talk about the THD, if you talk about the multi-level inverters, as I told, multi-level inverters, the THD is the byproduct, right? We can always use the filter to filter out the higher order harmonics which are there, because by using appropriate modulation technique, we have already eliminated third and fifth harmonic and seventh harmonic. That is the nearby harmonics to the fundamental. We have already eliminated to the larger extent, which is the most dangerous harmonic. So higher order harmonics can be filtered out with the help of a filter. So that is why. So current THD, we can reduce the current THD by using the filter.
Okay. Yeah, again, Pawan has raised one question in chat box. Are there any ongoing research or advancement in multi-level inverter technology that aim to improve its efficiency, reduce cost, or enhance its control techniques?
Yeah. Research is going on in all the domains that he have written. So
Okay.
this is a challenge as a power electronic engineers, right? We want to have small size. We want to have higher efficiencies. We have to have reduced cost. Whatever point you have written is point on point, right? This is the trend. This is the trend, right?
Yeah, if any other questions?
Yes, sir.
Ask.
Yes. So if we'll consider RL load, then the current density will depend upon the load only, na?
If you use RL load,
Yeah. Means for R, we'll get the same THD as the voltage. But
okay.
if we'll consider the RL load, then the current THD will be, means I'm asking the current THD is only dependent on the RL load only, no?
Yeah, you are saying that because in inductor, because if you are using RL load, the THD of the current will go down. Yes, that is correct.
Oh, okay. So
Yeah,
that's what I am asking.
yeah. But
Okay.
but 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 still we use a filter.
Oh, okay, sir.
Okay.
Okay. Thank you.
Thank you.
Yeah, good questions. Any again faster as posted. For high frequency switching, which semiconductor device is the best? GAT, FET, MOSFET, CMOS.
See again, this is a very that kind of question. You cannot select best, right? As our previous speakers have already shown in detailed comparison, it depends upon application, which application you are targeting.
Okay.
It depends on the application. Specific applications, specific device can have advantage, and specific device can have disadvantages as well. So you need to look into the application. What is the application for that?
Yeah. Okay.
Because there are many devices which are available in the market. What I will suggest you is to look into the data sheet. What is the data sheet? Or like industry do, their clients provide some specifications, as the first lecture of this FDP have started, where the guy from Tata Elxsi came. He told that the the company asked the client each and every parameter to the specification. So accordingly, they will choose the devices.
Okay. If any other questions? If anything not done, I like to say thanks to Dr. Shivam for a very high technical content in which the participants have asked more and more questions, and I hope they get clarified by your answers. Thank you, Dr. Shivam.
Thank you.
With this technical input, I would like to give you a virtual token of appreciation for this wonderful contribution to the FTP. Please accept this. Yes, hope able to see. Able to see, Shivam sir?
Yes. Thank you so much, sir. Thank you so much.
Okay, okay. So I'll also request the participants to turn on the camera for a few seconds, so that I can take a photo in the form of screenshot. Yeah, so most of them are open. Thank you. Thank you.
Thank you.